Okay, good morning everyone. So today we will first hour, we'll still try to finish the TDDB, and then in the later part we have the three group will have the presentations. So first we continue to talk about TDDB, and then now we are going to discuss the oxide breakdown models. So as we already explained in the last time that to understand the time dependent dielectric breakdown, we have the model that we call as a population model. So the population model can well explain the signal dependency. So if we have the TDDB effect, actually the thinner dielectric will have the fast time to break down, and then we can use the population model to have well explained, and also the concept related to the critical trap density and also the area dependency. So that's we already discussed in the last week. And when we talk about the TDDB, also we need to understand that there will be the different phenomenon related to the time dependent breakdown, which can be considered as a three different type of phenomena that we usually call as a soft breakdown, progressive breakdown, or the hard breakdown. So if you try to look at the typical current versus the time dependency, especially for the gate current versus the time. And then ideally, if we talk about the very thick dielectric, we have the phenomenon normally look like in this way. So first we have the current decrease, and after a certain moment we start to see the current increase, and this is normally only happen in the case whether we have the thick dielectric. But if we are considering the dielectric scaling, where we start to make our dielectric as smaller as possible, as thinner as possible. So in the case of a thin dielectric, actually we very often to see our current versus time characteristics start to change, and normally it will look like in this way. Still we have the current decrease, but after a certain moment we start to see the increase, a gradual increase of current, but not exactly reach to the hard breakdown. And after for a while we start to see the current shooting again. So that is actually the more realistic when you work on the TDDB reliability in the some of the advanced technology, especially the dielectric's approach to the very thinning. And from this curve, we usually would define the different phase. The first one is we see a small increase of current and then become noisy of a current, and that's where we define as a soft breakdown. And afterwards, as long as the time is longer enough, then we start to see in the end the current will start increase dramatically, and then we define this as a characteristic that we call as a hard breakdown. And in between the soft breakdown and then the hard breakdown, that we call as a progressive breakdown. Because between this period, the breakdown is gradually, progressively from the soft breakdown to hard breakdown. So that's why we call this as a progressive breakdown. So basically, once you start to test for the gate dielectric reliability, it's very often to see the curve. First, we'll have a soft breakdown, and then the hard breakdown, and then in between we have the noise. And this is really important TDDB characteristic. So once we have a population model, that also can help us to perfectly explain this phenomena as well. So just let me introduce again the population model. So as we already know, the electron trap are randomly generated in the dielectric. So that's why we need to introduce the concept of a probability, right? So we need to have the concept of probability to analyze the time-dependent dielectric breakdown. And therefore, we start to understand that if we have a dielectric as shown here, and first of all, since the trap are randomly generated during the stress, so if we apply the stress in this side, and we can start to see the defect or traps are randomly generated. So it can be at the first defect can be generated at here, and second one can be here, and third one can be here, and fourth one can be here. And as longer the time is longer enough, they will have the chance that your defect will be generated in the way that they can connect with each other. So, but basically this is still a random process. But in anyhow, it always has a certain probability that in the end, always the defect can be connected with each other. So once the defect is being connected with each other, so therefore we can start to form this conducting path for our electron. And then that still start to have the breakdown happen. So therefore, breakdown when conducting path is formed from anode to cathode. That's as I say. So that means that once the defect are randomly generated, and at one moment all the defect or traps are connected with each other, then we start to have the conducting path, and therefore we start to see the breakdown characteristic. And also, this population model can perfectly understand why there is a concept we call the critical trap density. Because as long as the defect is reached to a certain trap density, then it always can form the population path. So that's why in the population model, why we propose the population model, because we see there's a critical trap density, and once it reaches critical trap density, it always shows the breakdown curve. And also, why the population model are very effective to explain the thickness dependency, because if right now we have the thicker dielectric, if we have a thick dielectric compared to the case of the thinner dielectric. So in the case of a thicker dielectric, for sure, the time in the end to have the several defects being connected with each other, because it's randomly generated, so that means that we need to have a longer time to form this conducting path compared to the thinner dielectric. We only need 3 defects, so that means it's much easily to form the conducting path. So if we compare these two, for sure the thinner dielectric always has a lower time to break down, and the thicker dielectric is always has longer time to break down. So that's why we all believe that the population model are very effective, because it can be well explain the certain phenomenon that we have already seen in our experimental result, especially related to thickness dependency. So let's look at some of the experimental data. So this is a simulation. So we consider the simulation based on the population model, and this is a case where we consider oxide thickness is 8.9 nanometer, and also each defect, each trap, we consider the radius is a 0.45 nanometer. So in this case, so in the population model, we also have to consider the concept for the radius, the size for each trap as shown in here. So therefore, if we put these two numbers inside the simulation, we can find out that the simulation result fits the experimental charge to breakdown distribution very well. So that's one of the proof that why the population model is really existed in the TDDB issues. And also, we can have this thickness dependency can be well understood from the population model as well. So you can see this is a simulation result, and where we consider different oxide thickness. This is thicker one is 12 nanometer, and this is 3 nanometer here. And basically, we can find out that our oxide, as long as our oxide thickness is decreasing, then we always have the smaller beta. And if our oxide thickness is increasing, we have a large beta as well. And this is also related to the traps, how many traps to form the population model. So as we all know, the beta is a way to quantify the statistic distribution of this time to break down. So that means a larger beta. If we have a larger beta here, that means all of our TBD are more or less very uniform distributes in this small time scale. But if we have a small beta, that means our the TBD are widely distributed from this to this. And this can also be well understood by the thickness dependency as well, because if we have very thick dielectric, as shown here, so the time to form the conducting path needs so many defects and therefore the distribution will be much tighter because of it's not easy to form the conducting part. In this case, that's why our beta is always larger in the case of the thicker dielectric. But if we have a thinner dielectric here, because we only need the 3 defects, sometimes we'll probably only need 2 defects, or probably sometimes we can have a 4 defects. That's enough to form this conducting part. So therefore, the time to form the conducting parts here will be widely spread because of our dielectric is thinner. The defects that we need to form the conducting parts is relative small amount of numbers, so that will be more easily to form, and therefore our statistic results are widely distributed. So the statistic of population model explain decreasing of a Weibull slope. That means a large spread of the TDDB. Once we consider decreasing the oxide thickness, so basically we can use the population model to explain lots of phenomena we have seen in the experimental TDDB testing. So here is another experimental result. Try to understand the x-axis is oxide thickness, and then y-axis is a Weibull slope, beta here. So the decrease of a Weibull slope beta for thin oxide is an intrinsic statistical property of the degradation mechanism. So that means as long as we decrease our oxide thickness from the thicker one to thinner one, we always face the spread of our TDDB. We always face the issue that we cannot have a uniform time to breakdown characteristic. We always have the very wide spread of our time to breakdown. And because we also have the concept of critical trap density, so that means that as long as the defect has reached to a certain density, it is always have the time dependent TDDB results, and this is because that we have created the defect that reach to the critical trap density. So therefore, it will be interesting to understand that if we continue to decrease our oxide thickness here, then whether possible, there's always a limitation for our dielectric can make. So if you look at this is an experimental result from the 12 nanometer to the down to around 3 nanometer. So we can see as long as we start to decrease our thickness, and then our critical trap density is decreasing. And from these results, we can see probably once we thinner our dielectric down to below 0.9 nanometer of our oxide dielectric, then we only need one trap, we only need one defect to form the population part. So it's a very critical concern, because that also suggests that we cannot continue to decrease our dielectric, right? Because there is a physics limitation as long as we try to decrease our oxide thickness, but beyond certain nanometer, we only need one trap to form the population mass. So that means in anyhow, you will have very serious TDDB issues. So this is data from the left-hand side is from the one literature, and right-hand side is also another literature. Also doing the similar things, try to understand the oxide thickness versus our trap density. This is the trap density to reach to the breakdown. And from this experimental result, it suggests once you have a dielectric below 2.5 nanometer here, you always need very limited, probably like a 1 or even just below 1 to form the breakdown path. So that's give us a warning that we cannot further downscaling of oxide thickness because we only need one trap. That's enough to form the percolation path here. So the conclusion is that around at 3 nanometer, once we scale down of a dielectric below 3 nanometer, we only need one trap is to form the conducting path. But this is a huge warning because that means that we cannot further scaling our oxide thickness. We need to find some alternative way. Otherwise, there's only one trap to form the conduction path. So that means our dielectric is easy to have this TDDB phenomenon. And also, we can consider the way to calculate the trap generation. So the x-axis is our gate bias, and then the y-axis is a certain generation rate here. So this is a defect generation rate is based on the silk, where we already described before, where we already explained before what does mean the silk here. So based on the silk measurement, we can also try to calculate the defect generation rate, and we found out that the defect generation rate is exponentially dependent on our gate bias. In the case of gate bias below 5 volts, so exponentially increase is also very serious concern. So that means when we try to reduce our oxide thickness below 5 volts, the number of defects is exponentially increase as long as we stress from the longer time here. So that's also the one of the issue why to keep reminding us that if we try to fabricate the dielectric below 5 nanometer, we will start to face the lots of the reliability issue. So here is also another evidence try to prove that the Weibull slope is related to the critical trap density. So the x-axis is a critical trap density, and then the y-axis is a Weibull slope beta. So as you can see, once we have the thinner dielectric, and therefore we need to, the critical trap density is also decreasing. So once the critical trap decreasing, then that means we also get a smaller beta as well. Okay, so if we talk about the area dependency of the QBD, that's a charge breakdown. So basically the QBD is very similar to the time to breakdown. So we can consider these are more and less similar figure of merit to evaluate the TDDB issue. But in the past, we use QBD because of our dielectric is very thicker. But once we move to the thinner dielectric, and then we need to use the TBD as a figure of merit. So we can see the top one, this is oxide, TR equal to 11 nanometer. But the bottom is a TR equal to 4.3 nanometer. So now the conclusion is that if we try to consider the area from 10 to -6 to 0.1 centimeter square, and therefore the lifetime will drop around 3 to 4 magnitude for the 4 nanometer dielectric compared to only factor of 2 So that means here, this drop is huge. So this is a case of the smaller area on the thinner dielectric, and this is a big area on the thinner dielectric. So we can see the time to reach the breakdown is dropped around 3 to 4 orders if we have the thinner dielectric. But in the case of the very thick dielectric, we have the smaller area dependency, but that's good. So that means we fabricate a bigger device, then usually we will not suffer the TDDB issue. But if we try to fabricate a big device, but in the case with a thinner dielectric, we have the huge decrease of our lifetime. So this is also another evidence and another warning that if we keep only working on the oxide, silicon dioxide, and try to do the scaling, and we always face a lot of reliability issues, especially related to the time-dependent dielectric breakdown. So this is also another slide, but just try to tell us a very similar concept. In the last class, we already discussed the area dependency. So we can try to scale the Weibull plot by consider the area dependency here. And this is a case, we have the thicker dielectric, so that's 11 nanometer. We have the dielectric for the 4 nanometer here. So if we have a thick oxide, we always have a large Weibull slope and smaller area dependency. So that's good because we always want to have the large Weibull slope, because large slope, that means a very tight distribution, it's a good uniformity. But the ones we have a thin dielectric always face the issue with a small Weibull slope and also the large area dependency, so which is not good. Okay, so once we talk about the soft and progressive hard breakdown, so in the previous slide we have been already schematically drawn, but this is more realistic from the experimental data. So this is a typical gate current measured during the time-dependent dielectric breakdown testing, and you will start to see after a certain moment there's a small jump here. There's a start to getting noisy. Sometimes it's not easy if you try to plot this way, but if you try to plot as a way to calculate the current spread here, so now we can see there's a moment where the noise of the current is become large, as shown here, and then the noise is getting not only the increase of noise, but also increase this current spread at the moment it reached to the hard breakdown here. So based on this result, basically we can define this is a time where we call the soft breakdown. And the reason why we will have a soft breakdown is because this is the first creating breakdown path. Sometimes even there's a first breakdown path, but it doesn't mean the breakdown path is enough to completely destroy our dielectric, enough to have the huge current through. So now we will start to gradually getting more and more breakdown paths in the end to reach to the hard breakdown. So in between, this period is how we call the progressive breakdown. So this is exactly mentioned in here. So breakdown is not an instantaneous phenomenon. The leach current increase slowly after formation of the first breakdown path. So that's a typical things we see in our TDDB characteristic. And the reason why we have the soft breakdown, hard breakdown, and then that's our device will not immediately to have the hard breakdown is because of the breakdown spot is gradually formation. It takes some time. So it can be, for example, the first case, initial, we have very perfect gate dielectric. And at the moment, we start to form this small breakdown spot. And that's give us the first conducting path. And after as long as the time is longer enough, we try to, the defects getting more and more inside this conducting path. In the end, this conducting path is enough to allow all the current flow, and in the end, this will be the spot that all our dielectric values here. So that's one scenario. We always have the current go through in the one breakdown spot. But on the other hand, we can possibly to have the second case, whether we have the multiple breakdown spots here. So as usual, we have the first one. But because the breakdown, the defect is randomly generated, so it can be the second one and third one here. And some of the breakdown spot will growing bigger and bigger because we have a more defect formation layer. In the end, there's a one who first to show the breakdowns, the huge breakdown path here. So because we have so many small breakdown paths form, and that will lead to the, in the end, the hard breakdown. So in anyhow, if you look at for the current versus time characteristic, sometimes probably it's not easy to understand, but I believe if we try to understand by using the population model, by using the concept like here, I think it's pretty straightforward. I think everyone can quickly understand that the breakdown can be the first happen here, but it also can be second happen in the other region. And unless reach to the moment that the one breakdown path is getting bigger and bigger and then completely dominate the whole breakdown characteristic, and then we reach to the hard breakdown. So this is also important and can be well explained by the population model. So here is some of more experimental results here. So we can see this is a current versus a time in the left hand side, and this is a case where we have the oxide thickness of only 4.3 nanometer here. And this is the first one. This is a soft breakdown. And then if you try to zoom in here, this is a different scale. This is a larger scale. This is a smaller scale. So we can see this small hump here. Actually, if you zoom in inside, you will see the huge increase and very obvious of this noise can already observe here. So then we define this is a time where we call the salt breakdown time. So that's a T salt breakdown. And for sure, the last one is T hard breakdown. So usually the salt breakdown make classical detection of the breakdown problem. So basically we have the very huge problem try to detect the salt breakdown, because the salt breakdown is not that obvious that we can see compared to this one. So that's why we always try to use current noise. So if we see the current noise is increased, then we can define that point as a salt breakdown. And this is also another experimental result, try to understand the different bias that will cause a different time from salt breakdown to hard breakdown. So I think if you already have the mindset of the population model, if you try to understand how the things go in between the salt breakdown to hard breakdown, I think it should be very obvious to understand that this time between the SPD and HBD also is a gate bias dependency, because as long as we apply the larger bias, we should always generate the defect faster, and therefore the progressive breakdown time will be smaller. So this is an experimental result done when we consider the P MOSFET. And the P MOSFET, we give the negative bias. So this is a VG bias in between minus 3.8 volt to minus 2.8 volt. So let's look at the experimental result again. So this is a different bias. Minus 3.8, minus 3.5, and this is minus 3. So now we can see, for example, if we lower our gate voltage, this is a PMOS. PMOS, that means that less negative is a lower gate voltage. So if we lower the stress voltage here, for example, this one here. So, and now we all know this is time for the salt breakdown, and this is time to the hard breakdown. If we define the criteria like the current increase beyond a certain level, that's what we consider as a hard breakdown. Then this is the moment that the current increase beyond a certain level. So that's why we define this as a hard breakdown. So it takes 3,000 seconds here. But now if we increase the bias, this is minus 3.5 volt. Then this still the same. This is a salt breakdown, and this is a hard breakdown. But now we only need 100 seconds. So the wear out of a breakdown path progress gradually, and the rate is usually lower at the lower stress voltage, but the rate will be become larger if we have the higher stress gate bias. But I think that's pretty easily understood if you already understand the previous concept related to the population model. So also we can consider use a different way, try to understand this progressive breakdown. So that's basically depends on how you characterize your device. So in this line, we'll characterize as a current versus a time. But if you try to characterize with IG, VG, but after each moment, so that means this is a curve where we characterize in the sense we have a gate current versus a time. And of course, when we're doing the stress, first, our initial current is from here. And after a certain moment, it's become here. So that's a T equal to T0 and T equal to T1 here. So that's a phase 1 and phase 2. And then in the case of phase 2, if you try to already come back to characterize the IGVG, you probably already see the curve is changed. And this is the curve is a change at this region. And this is due to the silk. Stress-induced leakage current. So this is something we already understood before. So during the stress, if you have a certain defect generated, and then therefore you will see the current is slightly increased. That's we call as a stress-induced leakage current. But at the meantime, if we continue to do the stress, we will start to see the current will become like in this way. So this will be the region 3. So this is at the moment of T equal to T2. So this is T equal to 0, T equal to T, yes, this is T equal to 0. And T1, T2. So now, if you already see this noise increase, and you come back again to characterize IGVG, everything should be consistent. Then for sure, you characterize IGVG, you will see your gate current is increased in a very obvious way. So that's also another evidence related to the cell breakdown. And in the end, if you stress the time is longer enough, for sure you will start to reach the time of the hard breakdown. And once you reach a hard breakdown and you come back again to characterize IGVG, then you see your curve is completely changed, and now your gate current is super high because your device is already experienced with a hard breakdown here. So what I want to say is that actually, although it might be for you, it's the first time try to analyze if you don't do the TDDB testing in your previous experience. So that might be your first time to look at the time dependent gate current. But the important is that if you come back to characterize, this is IGVG is a static result. This is not time dependency. We just characterize this with a different time interval. Then we see the very consistent trend that the current will increase as well. So that's just try to make sure that what we understand, what we illustrate here, everything is consistent, no matter it's a time dependency characteristic or the static characteristic. We always see that the time dependent dielectric breakdown is gradually happening. And of course, the seems is that even we know the time dependent dielectric breakdown, we know at a certain moment of time, our dielectric will completely destroy. We will have a hard breakdown. But the most important is we need to find out the reliability margin. So the reliability margin is also in another way is our lifetime margin. So if you look at the characteristic like here, so first of all, we can start to see this, at this moment, we start to have a salt breakdown happen. But if we define our criteria for the hard breakdown, it's a 350 microamp here. So that means at this moment, we have the hard breakdown. But this also gives us a sense that there's a time interval in between, and this time interval can be our lifetime margin. So this will become very useful because this gives us a sense that once you start, because in the end, when we do the reliability, not only to understand the physics, understand modeling, try to improve the device characteristic, improve the device reliability. The overall, in the end, we need to do the prediction. We need to predict when the device will completely destroy, when the breakdown will happen in the what time scale, and that can give us some preparation. Just like in this case. This case means that once we see the first signal of the salt breakdown, the increase of a noise, we can understand after 100 seconds, the hard breakdown will come again. So that means we should be aware of that our device can be only used for another 100 seconds. So that's pretty important because that gives a sense of a prediction. That if we look at our device characteristic during the operation, we see the noise of our current, and this gives us a very useful warning that our device probably can only operate for another 100 seconds, another 1000 seconds, and we should stop using this device because otherwise the completely destructive will come in very soon. So that's the purpose, give us some lifetime predictions here. So in most of the case, once we see the salt breakdown happen, because the lead current is still very low, and then the device is actually still functional. So that means even we see the signal of the salt breakdown, but our device still can operate, our product is still fine. But the problem is that the time dependent, the leakage pulse is wearing out as a function of the time. So then we can foresee after certain timing for sure that the device in the end will face the hard breakdown issues. And then once it hard breakdown, the current will increase very fast and our device are not functional. And therefore, the time period between the salt breakdown and hard breakdown, in physical sense, we call the progressive breakdown. But in the reliability prediction, we consider this is our lifetime margin because that gives us a sense that how long our device can still be used, whether we should stop use this product or we can continue to use for another probably less than 100 seconds. So this is another concept that we call the impact of a progressive breakdown on reliability margin here. So now you can see the x-axis is a degradation rate. So generally the degradation rate is considered as a gate current versus the time. And then we can find out that this is a different stress voltage versus a different degradation rate, different how fast our current increase here. And this is experimental data at the 25 and 140 Celsius degree, and the different dielectric thickness give us a difference of the degradation rate here. So general conclusion is that if we stress at 4 volt, actually the current is increased so fast, it's more than 1 milliamp per second. But if we stress at 2 volt here, and then actually the current increase is very slow, it's below 1 nanoamp per second here. So if we can leverage this data, start to do the very basic reliability prediction. So if we try to consider the case of 1.2 volt, so this is a 1.2 volt, and then the degradation rate will be very limited. So probably will be the 10 femtoamp per second, right? So that means if we consider the criteria to reach a breakdown, that means if we consider the criteria is 10 microamp to reach the breakdown, 10 microamp as a hard breakdown criteria. So we can use this number start to estimate how long this rate can reach the hard breakdown criteria as a 10 microamp. So this is the hard breakdown criteria. So therefore, our lifetime for this device, which is equal to 10 microamp over 10 femtoamp per second, right? So that's a very basic mathematics, but that's already give us a certain very useful prediction. So that means in this case, our lifetime for our dielectric is longer than 10 years. So that's the purpose in the end. Just a reminder that in the end, our purpose is somehow develop the way that we can do the prediction. We are not only understand, we're not only do the testing, try to destroy our dielectric. We're not only do the statistical modeling. We are not only try to understand, but in the end, we want to have the method to predict the lifetime, because this lifetime, and also this lifetime prediction is not just based on the pure, for example, pure mathematical calculation without physical sense. But this prediction is really have the physical meaning because we consider the degradation rate, and we believe this degradation rate is makes sense based on the population model. So everything is a physical based approach, and that gives us a very useful and somehow, because this is a physical based approach, sometimes we consider physical based approach is more reliable. It has a physical meaning inside, and in the end we can use this way to predict our lifetime. And then we tell our customers that we have this product, we have a product with a 1 nanometer dielectric, but if you operate at a 1.2 volt, you don't worry about lifetime because you can use this product for more than 10 years. That's exactly the customer want to hear, because he wants to know what would be the condition he can use for a certain time. Okay, so last is the acceleration model. So when we talk about acceleration testing, we have been already previously talked about what does mean the acceleration testing. So acceleration testing is that we try to accelerate the degradation, and then we use this accelerating degradation, and we have a certain model to predict the lifetime. So basically, we have the two different cases. One is the thickness is larger than 5 nanometer, and the bottom one is the thickness below the 5 nanometer. The reason why we have to divide by this thickness is because we believe below 5 nanometer we have a direct tunneling. Because our thickness is too thin, so the current is completely tunneled through our dielectric without influence without the dependency of the electric field. Actually, right now, it's mainly dependency on the voltage. So that's why our lifetime model is based on the voltage. That's we talk about the voltage model. But on the other hand, the F-N tunneling is happening in the dielectric is more than 5 nanometer here, and then therefore the electric field injection from the one side to the another side is mainly determined by the effective electrical strength in the dielectric. So therefore, the model is dependent on the electric field, where we can see the time-dependent breakdown TDD is correlated with electric field. This is because due to the F-N tunneling here. And here is some more detail related to the physical model. Some people say the 1/E model is related to the N-hole injection. The E model is related to the thermochemical, and voltage model is related to the hydrogen release. But nowadays, I think this physical model for the defect generation sometimes is not that exactly true, because there are so many reasons will influence the defect generation. But what I believe is true is this tunneling mechanism to determine our acceleration model. I think that still nowadays pretty makes sense. So let's look at some of the experimental results. First of all, this is the field acceleration law. We have the 1/E model. So then our TBD, time to breakdown, is correlated with our 1/, electric field. So that's why we call the 1/E model. And this one is E model here. So we can see the bottom, this is E model, and then can fit the TBD very well. And this can fit the TBD very well in the sense of a 1/E model. And once we have this, this one and this one is fit with this data in this region. Because we only test, we want to our degradation happen faster, so we will test in the high voltage to accelerate the degradation. So that's why we call it accelerating testing. But even we try to fit very well in this region, but once we try to extrapolate, we will still see some spread of this fitting toward the low bias region, because our real device is actually operated in the low bias. And for example, if you use a 1/E model, in here you will have the fitting like here. If you use a 1/E model, you will have the fitting like in this way. And how do we understand which model is correct? That's always an issue, even in nowadays, because our technology is getting evolved very fast. And then once we use another dielectric, we have to come again to understand the model, and we have to verify the model. And to be honest, even in the silicon dioxide, still the debate which model is correct, because this is a timing. For example, this is a time. What our target to extrapolate lifetime is always want to make sure our TBD is more than 5 years or even 10 years, depends on application. So in anyhow, you cannot possibly to verify the result here, because it takes a 5-year stress, it takes 10 years stress. And what usually people do is doing the very low voltage and try to stress. As far as I know, some people doing like the yearly base stress, they stress the result for 3 years, try to verify the result. But even though the stress 3 years probably will be somewhere here, so it's always very difficult to verify the result. But that still gives us a certain interesting reference here. So nowadays, we don't actually have the conclusion that which model is correct, because this need to be carefully used once we consider the physical reason. For example, if we consider 1/E model, it needs to fit the degradation is based on the anode-hole injection. If we consider 1E model, it needs to fit the physics is based on the thermochemical model. So that's the only things we can make sure that our model can be correctly used. And of course, once we do the scaling, we will completely change the scenario. So the oxide thickness beyond 5 nanometer, that's a F1 tunneling. So in here, that's why, because electric field determine the electrons injection. So that's why we can use E model or 1/E model. But on the other hand, once our thickness below 5 nanometer, the gate bias determines, and now it's become the voltage acceleration model. So this is a case, in the case of oxide thickness below 5 nanometer, so we can see the power law model based on the voltage acceleration here can fit the data very well. So this is a oxide thickness between 1.3 to 5. This is oxide thickness between 1.2 to 5. And also, if we consider the different gate bias, actually we will start to see the correlation. For the thinner oxide, the TDDB correlates better with VG than with the electric field. So that's also another interesting viewpoint. That's because due to direct tunneling. So you can see this is a time to break down, and then with a different oxide thickness, and this is a gate voltage versus time here. And also, once we do the acceleration, we also need to consider the temperature acceleration as well. So now you see, this is a case with a different oxide thickness. And if we down to very thin dielectric here, actually our TDD is dramatically decreased. So that's also another warning that why we cannot continue to scale our oxide thickness, because now we have very strong temperature dependency for the ultra thin oxide. So in the end, the goal is try to make the plot like in this way. We can extrapolate the time to break down with a certain criteria. So this is a criteria. Usually this one is a 10 years. So we have the 10 years here, and we test our dielectric in the different temperature. This is 25 Celsius degree, this is 100, this is 150, and we test at high voltage because of we want to have the acceleration testing. So once we test at the high voltage, we start to extrapolate to the target lifetime for the 10 years. So for example, in this one, we can see this voltage, which is 3.2 volt. And this voltage is 2 volt. So that means the device, if we use a 3.2 volt, ideally, the device, the dielectric can sustain for more than 10 years lifetime. This is at a 25 Celsius degree. But if you look at for the 150, oh no, this is 200 Celsius degree. So that means for 200 Celsius degree, we can only apply 2 volt, and our dielectric can be used for the 10 years. So that's actually in the end is a goal for this acceleration modeling, because in the end we want to extrapolate the operation voltage that can reach to the 10 years lifetime. So these are the operation voltage. So that's in the end is our goal. So this will be also the interesting comparison. For example, if we consider this is a 11 nanometer dielectric, and we use a 1/E model and E model to do the lifetime prediction here. And the condition is we consider only the intrinsic breakdown distribution predict at 4 megavolt per centimeter, with both using the E model and 1/E model from measurement at the 10 megavolt, because we do the stress, so we do the acceleration testing, so we will test at the 10 megavolt. But now we found out that the 1/E model predicts the infinite lifetime. You can see if we use a 1/E model, actually our lifetime is longer than the universe here. So that means the 1/E model is not make sense in this prediction. So because the 1/E model is based on the L10 tunneling mechanism here, but this is a 11 nanometer. So at this moment, the 4 megavolt, this is a low field. So L10 tunneling is small. So that means this prediction is not valid. So that's why when we do this lifetime prediction, we not only have to understand the model, we also have to check the extrapolate result makes sense or not. And because we need to understand the physics behind based on this acceleration model, because that sometimes might give us some misleading result if the physics is not correct. So the conclusion is that for low field, the current via L10 tunneling are quite small. So 1/E model is not valid at a low field condition. So that's also pretty important. So as already said in the pretty early beginning, once we consider reliability is a multidiscipline subject that both need to combine. For sure, we are the semiconductor guy. For sure, we need to very familiar with semiconductor device physics, but we also need to understand the reliability physics. And also we need to start to use some mathematical tool in the end to do some calculation prediction. But overall, we still need to come back to check the physics, whether our degradation mechanism really fit our condition or really does happen in our device or not. So when we do the reliability prediction, one of the things is that we need to do the percentage scaling as well. So in reality, this is a real spec that mainly come from your customer. Your customer want to know what actually is the criteria can reach for 0.01 percentage value at a certain area for 10 years here. So now we have to apply the Weibull distribution, try to calculate the result based on the customer's target here. So the first one is we will have the what we call the area scaling. As we always stress at a small device, because we want to focus on the intrinsic reliability, so we always stress on the small device. And then first of all, we scale to larger device. So that's a area scaling. So that's a first step. And if you still remember, when we try to calculate the Weibull plot at the y-axis equal to 0, the time is equal to actually is equal the t is equal to the value for 63%, as shown here. So this is the time TBD for 63%. But now we have to do the scaling, do the calculation again from 63% shift to 0.01%. So now this is 0.01. Because for sure, the customer won't interested in the 63% value time. Will be only interested in the value percentage that extremely small. So that's a 0.01% here. So this is actually the themes here. First, we do the area here. And second, we do the percentile. Of course, in here I just ignore the temperature, so I mainly focus on the data coming from 150 Celsius degree. So we do the testing and 150 Celsius degree. We have this data set here. Then we can shift to the left due to the area scaling, and then shift to the left again due to the percentage shifting here. And then in the end, we can extrapolate this value. This is the operating voltage. For 0.01% value with 10 years. In 0.1 centimeter square device area. So then it's 1.5 volt. So this is exactly in the end what we do is we test. You can see now we test at a very high voltage. We test at a 4 volt, 3.5 volt, but we'll fit it. This is fitted by the acceleration model. And then once we fit it by the acceleration model, so we can start to see the value here, and we do the area scaling, we do the percentile scaling. In the end, we reach to this term here. So now I hope you understand why in the previous previous paragraph, previous lecture, we spend the time to explain the area scaling. We spend the time to explain the Weibull distribution, and also now we have to use the acceleration model, because in the end is we want to have this figure. And this figure is important. If you look at all the data sheet, all the company report, they always use this way to convince their customer why their product can use for 1.5 volt for 10 years. Okay, so finally, we compare the 2.8 nanometer versus the 10.8 nanometer. This is a 10.8 nanometer. So if we do the same scaling to our target, it's only 1 order decrease. But if we compare to the 2.8 nanometer, we have the 8 order decrease. So you can see the drop lifetime at fixed gate voltage due to temperature, area, and percentile. We have a 1 order magnitude decrease for 10.8 nanometer if it's from the experimental result in the end to shift to our spec. But we have the 8 order of magnitude shift from 2.8 nanometer to our targeting spec. And this actually shows that the oxide reliability is a potential showstopper for the lifetime, for the further downscaling. So that's why from this result, it proves that we cannot use a very thin dielectric in our product because in the end, we don't have any useful lifetime. We need to replace our dielectric to the other material. For example, that's why later on we have a high K metal gate. We put a certain different high K dielectric on top of SiO2 because in the end we want to improve our gate reliability and gate lifetime. Okay, so this is a summary that for your own reference you can try to check out. And of course, still lots of the concept here is still under the debate, especially related to the extrapolation law and acceleration model. There's still lots of people nowadays they are using the different way to do the modeling. But anyhow, this is a good starting point to have a general overview of what's the status of the TDDB. Okay, so now we will stop here and we will start to move for the group presentation. So we will come back in the 5 minutes later.